Okay, today we're going to be talking about radiation damage and prevention. We're going to start off with what it is, and then go to what it does and how to prevent it. So first off, we're going to do a quick review about what it is. Radiation is different forms of high-energy particles or rays that can penetrate and damage the matter with which it comes into contact. It comes from radioactive or unstable elements. These are elements with atomic numbers above 83, with the addition of technetium and promethium. And each are elements that spontaneously destroys part of its mass to emit radiation in the form of either alpha, beta, or gamma rays. And so we'll start off with a quick review of what these forms of radiation are, and I've posted some links at the end to give some further information if you'd like to dive a little bit more into how each of these are produced. So the first is alpha ray. These are the largest form of radiation, and it's when 2 protons and 2 neutrons are released from the nucleus of a radioactive element. And these are basically helium nucleuses. The next is beta rays, and they're essentially electrons that are formed by the nucleus as it decays. Like it was stated, these are formed in the nucleus and don't just emit from the shells of electrons that are generally found in these atoms and in elements, but are actually created during that decay process and are shot from the nucleus in the form of beta rays. The third is gamma rays, which are high-energy photons that come from the de-excitation of a nucleus. These are similar to an X-ray, except that X-rays come from the de-excitation of an atom. So, radiation, we've commonly seen it in use in different forms of technology and commonly in medicine, used for chemotherapy to treat those with cancer. Radiation can also have some pretty negative effects on our bodies. Basically what's happening is that each of these particles have ionizing energy. This energy, when it comes into our cells, can break covalent bonds between the double helix of the DNA strand. And so this DNA strand can break, which obviously is harmful. So we've got some PowerPoint magic to show this. Is the beta molecule, the beta ray is coming in, it's hitting our double strand and then causing it to break. Generally this wouldn't be too much of an issue because we have different mechanisms and different enzymes that are there to repair it, but this radiation can also oxidize the different mechanisms, the different molecules that would be there to fix it, which can cause permanent damage to the cell. When this happens, one of 3 things happen. The first is called senescence, which is an irreversible state of dormancy. I like to think of this as just the cell is going to sleep permanently and it never wakes up. So it's still there, but it's not helping with our biological functions and it's not really useful anymore. The next one is the cells committing suicide, which is known as programmed cell death. So it's gone. And then the third way, which is the most harmful way, is unregulated cell division, which leads to tumors and cancers. And as we can see, it just keeps going and going unless we use radiation again to fight this. So kind of ironic that what causes cancer is also our main way that we fight against it, but that's how it is. So now we're going to deviate a little bit and we're going to talk about how we measure radiation doses, because this is going to help us later discuss the effects that it can have on our tissues and our bodies. So first off, 1 radiation dose unit is the simplest one, and it's measured as 0.01 joules of ionizing energy when deposited into 1 kilogram of tissue. What this equation is showing us is that the more concentrated the dose is, or the smaller the area that the dose is in, the more damaging it can be. So for an example of this, if a 50 kilogram person absorbed 1 joule, this would be equal to 2 radiation dose units. However, if that same person in their 2 kilogram arm absorbed that same amount of energy, it would be 50 radiation dose units, so much more damaging. The next one is called the gray. This is 100 radiation dose units, and it's just an easier way to quantify it as a radiation dose unit is so small. The next one is the Roentgen equivalent man, which is the radiation dose unit multiplied by the relative biological effectiveness. And we see that from this chart here, that different sizes of rays produce different amounts of damage. And this makes sense, it's intuitive. As an alpha ray being the largest, it would have the most charge on it, and more charge means more ionization and could cause the most damage. Whereas gamma rays and X-rays and very small beta rays wouldn't cause nearly as much damage. So, when these are put together, this gives us the SI unit that we use, which is called the sievert. Sievert is that relative biological effectiveness multiplied by 100 radiation dose units, or 1 gray. And this will help us to quantify different amounts of exposure that people can have. So here's a chart in sieverts. 0 to 0.1 sievert has no observable effect. And then as we continue to go through, we start to see reversible effects, and then resulting in irreversible effects and permanent damage, and then death. This next slide shows the average yearly dose that a person will encounter in Australia, Germany, the United States, and then the world. As we can see, this is millisieverts per year, whereas the previous one was in sieverts in one single dose. So as we can see, even in the United States, which has the most, at least in this chart, it's only 3.5 millisieverts per year, so well under the range where it could have been damaging or cause permanent problems. However, though, there are people, such as researchers, clinicians, and nuclear power plant workers, who are exposed to much greater levels of this radiation. And so there are a couple things that we can do to protect them against this radiation, so that they don't have those very adverse effects just by working where they work. So the first one is to limit the time. This may be obvious, but like we said before, the more concentrated a dose is, the larger the effect it has. As we reduce our time, we give ourselves more time to repair themselves before the effects become irreversible. The next one is to increase the distance. This is easy to do for alpha particles, as they can only go through a few centimeters of air, or less than a millimeter of biological tissue. For beta particles, it's still pretty easy, as they can penetrate about a meter of air, or tens of centimeters of tissue. Gamma rays, however, just like X-rays, can penetrate many meters of air and meters of concrete, and so are much harder to just increase our distance from when we're talking about an office workspace, such as a dentist's office or things like that. So when it comes to X-rays and gamma rays, generally the most effective thing that we can do is to use shielding. And we see that in this picture here, is that gamma rays can only go through several centimeters of lead as opposed to several meters of concrete. So we'll often put a lead apron on the person getting the X-ray, and then the one administering the X-ray will often stand behind a very thick door or a wall or something that will help them to not be exposed repeatedly to those high doses of X-rays and gamma rays. With these three ways, we're able to reduce, for the most part, exposure so that it's under the federal regulations for exposure and keep all of these different people safe. So, that's all we've got. Thanks so much for listening. If you want any more resources or any more information, here are some different sites that I got some of my information from, and that can lead you to even greater sources about, if you want to dive deeper into the effects that radiation can have, or how alpha particles or beta particles or gamma rays are produced, or different things like that. And then here is just the sources for those fun animations and those fun pictures. So thanks so much again for listening. I hope you found this informative. Have a great day.